finish these orbital diagrams and orbital energy diagrams. So, pi 2 and pi 3 are both going to have a single node here. We can either put the node straight down the center, vertically, or we can put the node straight through the molecule horizontally. But if we put the molecule horizontally, those two carbons that the node passes through will not contribute to the orbital. So how many net bonding interactions do we have in pi 2?
4.
So we've got a bonding interaction here and a bonding interaction there. And we've got a bonding interaction here and a bonding interaction there.
Yeah, 4 bonding interactions.
Well,
But I know we have 2 anti.
We also have 2. So we have 4 bonding and 2 anti-bonding. So we have 2 net bonding. And the net bonding is the one that actually matters. 2 net bonding interactions is fewer net bonding interactions than pi 2 from the acyclic system, but more net bonding interactions than pi 3. So that energy level is going to be somewhere in between pi 2 and pi 3. And because these both have one node, they're going to be at the same energy. So pi 3 has dropped in energy, but pi 2 has actually risen in energy. But what you'll notice that does is it lowers the energy of 2 of the bonding orbitals, pi 1 and pi 3, while raising the energy of only 1 of the bonding orbitals. So 4 electrons go down in energy, 2 electrons go up in energy. That's better. The other thing you'll notice is that there are only 4 energy levels. And because there are only 4 energy levels, the gap between them is bigger. So this HOMO-LUMO energy gap here, this delta E, is significantly larger for benzene rings. And that actually has implications for the ultraviolet visible spectroscopy of those two systems.
Should it be 4 and 5?
That's 5. Terribly wrong 5. My 5s and my 3s are indistinguishable. How many net bonding interactions are there for pi 3? Just 2. Because this orbital is too far away to interact with that one. Because the carbon's in the middle, and this one's too far away. That was required anyway, because if the orbitals are going to be degenerate, they probably have the same number of net bonding interactions. So you notice that pi 2 rises in energy because it has fewer net bonding interactions than pi 2 in the acyclic system. But pi 3 drops in energy because now it has 1 more interaction. So there's the net stabilization. These effects kind of cancel each other out, right? Pi 3 drops, pi 2 rises. The real aromatic stabilization energy is in this drop of the pi 1 orbital. So as usual, right, this is the stability orbital, the one down the bottom. But if you want to react, these are the reactivity orbitals. So when benzene reacts with an electrophile, it's reacting through one of those 2 orbitals, right? The HOMO is degenerate. Pi 2 and pi 3 are both the HOMO. So what about pi 4 star and pi 5 star? I'm not going to be able to draw them up there because everybody has mass. What do these guys look like? I many nodes do they have?
Two.
2 nodes, right? 0 nodes here, 1 node here, 2 nodes there, 3 nodes there. How can we put 2 nodes through molecules? Well, one way is to have both a horizontal and a vertical node. So it's like the anti-bonding version of pi 3, right? It's completely arbitrary which one of these is pi 2 and which one of these is pi 3, or which one of these is pi 4 star and which one is pi 5 star. Those 2 nodes are orthogonal to each other. They have to be. And we've got an antibonding interaction here and an antibonding interaction there. So we've got 2 net antibodies. How else can we put 2 nodes through the molecule, have those nodes be orthogonal to each other, and generate 2 net antibody interactions?
Can you put them straight, like both through corners? Oh, okay.
We could draw an X instead. We could put them both like through this, like here,
Yeah.
but then that would be the same orbital just rotated.
Oh, I meant to put both of them, but then it wouldn't be orthogonal, so never mind.
In math terms, these orbitals are eigenfunctions of one another.
This is terrible. We're bringing differential equations in linear into organic chemistry.
Yeah, I know. It's unfortunate.
It really is.
So what we have is we have 4 antibody interactions and 2 bonding interactions. Right? So the net bonding is 2 net bonding, which means these are degenerate orbitals of 1. So we have either 6 bonding, 2 bonding, 2 antibonding, or 6 antibonding. We don't have odd numbers. So instead of it changing by 2 net bonding interactions each time we move up an energy level, it changes by 4. It goes from 6 to 2, then it goes to -2, then it goes to -4. Bigger energy gap. That shows up. The lambda max is 268 nanometers for this because that energy gap is smaller than the lambda max for this one. 264 nanometers. So we have a shorter wavelength, higher energy transition for putting an electron from the HOMO of the benzene ring into the LUMO than we do from putting it from the HOMO of the acyclic system into the LUMO. So we know that these energies are further apart by looking in the UV spectroscopy. The use of UV spectroscopy, which we're kind of skipping, in organic chemistry, is to determine the extent of conjugation of the system. The more conjugated system, the longer wavelength. If you just have a single double bond, it's about 171 kilocalories per mole. And then if you have a diene, it goes up to about 220. Right? And then if you have a triene, it goes up to maybe like 270. It goes up by about 50 nanometers every time you increase the length of the conjugated system by 1. So if you're going to go to a tetraene, it would go up to about 230, roughly. So it's kind of 50-ish close. And then if you put a benzene or like a methyl group on there for hyperconjugation, that changes it, it makes it go up by about 5. So conjugation raises the wavelength of the absorption by about 50. Hyperconjugation raises it by about 5. And so you can start determining how long your conjugated system is and how substituted your conjugated system is. That's where it's going. So this is just the energy diagram for the benzene, and what I will ask you to do on the quiz on, what's today? Thursday? I will ask you on the quiz on Thursday is to explain the origin of the aromatic stabilization energy by drawing these orbital systems and comparing them to one another and basically doing exactly what I just did. So hopefully you'll be able to arrange that. So we generated this energy diagram by drawing all these orbitals. What if you don't want to have to draw every freaking orbital in order to figure out what the energy diagram looks like? Is there a shortcut? And so if we wanted to draw the orbital energy diagram for the cyclopentadienyl system, with the cycloheptatrienyl system, we didn't want to have to figure out how to sketch every orbital. The shortcut is to draw a circle and then inscribe the polygon within it with a vertex at the bottom. And wherever the polygon hits the circle is where your orbital energies are. It's very important that when you do that, you put a vertex at the bottom, because there's always going to be a single non-degenerate orbital down at the bottom. And then the p orbitals just go through the center. And then you fill up your orbitals. So all you wanted to do was draw the orbital energy diagram for benzene, and you didn't have to sketch the orbitals. You would just do this. Describe your polygon within the circle, wherever it hits. You'll notice they're pretty evenly spaced, and your hexagon is a nice clean hexagon. So what about pyrrole? What would the orbital energy diagram look like for the pyrrole? And then we can worry about what the orbital would look like.
Why does this circle thing work?
Because the bottom orbital doesn't have any nodes, right? So you've got that one vertex that's kind of by itself. And then every other set of orbitals is degenerate. So you're going to have the two sides of the polygon kind of going up to the same
I guess my question is, can we use that with like any
Yes.
ring? Okay.
Well, any single ring, right? If you have bicyclic structures, it really doesn't.
Well, that's what I meant.
So if we do a pentagon, in the ring, you draw a decent pentagon. We're going to predict it's going to look like this. Pi 1, pi 2, pi 3, so we're going to degenerate. Pi 4 star, pi 5 star. And it's a 6 pi orbital system, or 6 pi electron system rather, 5 pi orbital, 6 pi electron, which means that we have what we call a closed shell here. No unpaired electrons. All the bonding orbitals are filled. And all the anti-bonding orbitals are empty. That's what we want. What else do you notice about this diagram? Besides the fact that it's a closed shell.
It's not symmetrical in regards to like the p orbital level, so like the 2 and 3 are closer, and the 5 pi whatever.
So it's not symmetrical. Because we have 3 bonding orbitals and only 2 anti-bonding orbitals, pi 2 and pi 3 are significantly closer to the original p orbital energy level than pi 4 and pi 5 star away from them. And that's going to be true anytime you have an odd number of pi orbitals. What that implies is that pi 2 and pi 3 have fewer net bonding interactions than pi 4 star and pi 5 star have net anti-bonding interactions. So that's what it looks like. We got a nice closed shell. And this molecule is actually isoelectronic. With the cyclopentadienyl anion. The cyclopentadienyl anion is also aromatic. And that manifests itself really unusually low pKa to the sp3 hybridized carbon hydrogen bond, right? That sp3 hybridized hydrogen there has a pK of 16, which is ridiculously lower than any other sp3 carbon hydrogen bond, right? Compare that to the CH3 group of the alene, right, with that pK of around 40. Compare that with the CH3 group on a benzene ring, the benzoic position, pK of around 39, no, sorry, 41 for benzoic. So those change by 9 or 10 orders of magnitude over an ordinary sp3 CH bond. And this changes by 34 orders of magnitude over a regular sp3 CH bond. Making this anion aromatic is a much more important. And that's consistent with the 30 kilocalorie aromatic stabilization energy, where its conjugation only changes by about 2.5. So quite acidic. On the other hand, SN1 reactions of this group, if we just heat this up with a solvent, right, deposilate with water, this is a slow reaction. Carbohydrate intermediate is not very stable. And that is because the carbohydrate intermediate is anti-aromatic. Cyclopentadienyl anion is stable, but cyclopentadienyl cation is not. So what does cyclopentadienyl cation look like? It's a cyclic pi system. We have 5 contiguous sp2 hybridized carbons. But the energy diagram doesn't have a closed shell. It has 2 unpaired electrons because pi 2 and pi 3 are now only half filled. It has 4 n pi electrons. Makes it anti-aromatic, which actually makes it less stable than it would be if it were not a cyclic pi system. The energy rises for an anti-aromatic system. Cyclopentadiene itself is non-aromatic. In order to be either aromatic with 4n plus 2 pi electrons or anti-aromatic with 4n pi electrons, you first have to be a cyclic pi system. If you're not a cyclic pi system because there's an sp3 hybridized carbon in there, then you're non-aromatic. And you've got to be planar, right? You can't be either aromatic or anti-aromatic without being planar. Because otherwise the p orbitals don't overlap with each other because they're not, you don't have an out-of-plane p orbital on each atom. So an open shell like this is associated with an anti-aromatic compound, and a closed shell of all paired electrons is associated with an aromatic compound, and that's where the 4n and the 4n plus 2 comes from. Right? The plus 2 is these 2 in the non-degenerate orbital. So what would we expect for the 7-membered ring analogs? Would we expect that pKa to be comparable to the cyclopentadienyl system? Well, as it turns out, that pKa is only about 39. So we don't get an aromatic stabilization for our anion. We actually have a 4N system where N equals 2. There are 8 pi electrons in there. That's an anti-aromatic system. Heavily stabilized by resonance. There are 7 resonance structures for this. So you can actually spread that negative charge out on every carbon by drawing the resonance structures, which is why its pKa is as low as it is, at 39. But it doesn't have the aromatic stabilization energy because it has an open shell. By contrast, the carbocation intermediate is aromatic. Where n plus 2 with n equals 1, 6 pi electron system. So this is a very fast reaction. So it's the opposite. For the 5-membered ring, the anion is aromatic and the cation is anti-aromatic. For the 7-membered ring, the anion is anti-aromatic and the cation is aromatic. What does that orbital energy diagram look like? Well, you can probably guess what it's going to look like by analogy. We're going to have one orbital that's down here, pi 1, and then we're going to have a pair of degenerate orbitals. And then we're going to have another pair of degenerate orbitals. And then we're going to have another pair of degenerate orbitals. So there's going to be no nodes, one node, 2 nodes, 3 nodes. Where are the original p orbital energies relative to this diagram?
Between the pi 2 and 3 and the pi star 4, right?
So between the 1 node and the 2 node orbitals, which one are they closer to?
The 1 node? 2 nodes? I don't know.
There's 3 bonding orbitals, there's 4 antibonding orbitals. Because there are more antibonding orbitals, the p orbital level has to be closer to the antibonding. Why? Because the sum of these 3 energies has to equal the sum of those 4 energies. Because the sum of the 7 energy levels altogether has got to be equal to the sum of the 7 p orbitals it came from. So you'll notice that the carbocation looks like this. But the carbanion is an open shell. Looks like that. Actually has 2 unpaired electron up in the antibonding orbital. So this is an open shell. On one of the pre-recorded videos, I actually went through the cycloheptatrienyl system and drew all the orbitals, so you can see exactly what those orbitals look like. Remember, you can, if you're good at drawing, right, you can use the whole describe the polygon. And if you describe the polygon, it becomes even more obvious that these are closer to the middle of those, and because the p orbital energy level cuts the circle exactly in half. If you're not very good at drawing, describing a regular heptagon inside a circle might be more of a challenge than just a regular way the energies are. But it works. So we've seen that you don't have to have an even number of atoms in your ring, and they don't all have to be carbon. Anytime you have a contiguous set of sp2 hybridized carbons in a cyclic system, you can either be aromatic or non-aromatic, or aromatic or anti-aromatic, depending on how many pi electrons there are. And that's it. Because we are at time in this 10:10 section. So we'll work more with aromatic systems, and I think on the schedule for Thursday is electrophilic aromatic substitution. It's the big reaction of the aromatic system, and so we'll be going through a bunch of different examples of electrophilic aromatic substitution and then some synthesis.